That's what I'm supposed to tell you. Yes, correct. This meeting is going to be recorded. Thanks. We have a PhD defense today. My name is Jens Klingman, and I'm going to be the chairman of this session. We have an audience here, which is actually, considering the circumstances, quite large. Thank you for being here. And the purpose of this is the PhD defense of Sara Månsson, with the title "Spot the Difference on the Way Towards Automated Fault Detection in District Heating Buildings." We have more people, important people here. We are very grateful to have an opponent and a grading committee. And the faculty opponent is Professor Svend Stensen from DTU in Denmark. We have a grading committee, Professor Natasha Nord from NTNU in Norway. We have Dr. Per Rosén from E.ON in Sweden, and Professor Victoria Martin from KTH, also Sweden. At this point, I would like the faculty opponent and the grading committee, please acknowledge that you hear this and that the sound quality is good.
Hello, this is Victoria. I can hear you well. Quality is very good.
Yeah, I also hear very well. Thank you.
Natasha Noor here. I hear and see everything well.
Perfect.
Here, and I also have perfect sound.
Okay. We have Robert Sass being in charge of technology here, and he seems very calm, so I think this will go very well. We also have an agenda, and I will start by asking Sara, is there anything that you would like to comment that is wrong in your thesis that you want to point out? Then this could be a perfect time.
There is actually one thing, and that is that the fifth paper of my thesis has now been published, and I'm just gonna show you that here. There, so we published this paper in Energies just a few days after we published the thesis, actually. So that is the errata that we have for the thesis.
Okay, then thank you very much. And then we're going to go through this very quickly. We're going to have the respondents' presentation. So Sara's going to make a presentation. And possibly we're going to have a short break after that. And then we will have questions and discussion to begin with between Sara and the opponent. And then the grading committee will be given the chance to ask questions. And finally, the audience, which means both people being in this meeting or physically at this place. And that will end the open session. After that, we will have a grading committee meeting, which is closed. So the audience here, I will have to ask to leave. And the grading committee will have a meeting where also the Sara supervisors will participate. Okay, then we can move on to point 2. Sara, ready to present?
Yes. Okay, just going to change the PowerPoint slides. There. Okay. Before starting my presentation, I just want to say thank you very much for all the people being here today. And of course, also to the grading committee and the opponent for being part of my PhD defense. And of course, also a big thank you to Vito, who has been financing my project throughout the last 5 years. As Jen said, today I'm going to present my thesis, which is called "Spot the Difference on the Way Towards Automated Fault Detection in District Heating Buildings." And before starting my presentation, I just want to show you this illustration here, because this is the illustration that I have on the front cover of my thesis. And it's actually a bit of a reference to the title, because what I have created here is a game of Spot the Difference. when you're giving two images that are kind of similar, but there are still some differences in one of them that you are supposed to spot. And this is exactly what I've created here. So before starting the presentation, I simply wanted to present the solution to this game of spot the difference. So in the right picture, we have some differences. They are not necessarily related to district heating maybe, but it still shows the purpose of the game of spot the difference, I think, in a nice way. However, I mean, the work that I have been doing in my work is to actually spot the differences in the district heating systems. So that is, of course, what I'm going to talk to you about today. Before talking more about the results and so on, I just want to show some basic concepts about district heating. If you look at this picture here, we can say that this is a simplified illustration of a district heating system. At the top, you can see that we have some sort of production of heat. Then we have the blue and the red lines, which corresponds to distribution of heat. And then we have the buildings in the system, which corresponds to the consumption of heat. And the blue and the red line also represents two temperature levels that are important. The red line represents the supply temperature, which is the temperature of the water going out from the production site and into the buildings. And then we have the blue line, which represents the return temperature, and that is the temperature of the water going from the buildings and out to or back to the production site. Since I have been working with buildings, I also want to show you this picture because this illustrates what's located inside the buildings. So we have an internal heating system and we have the customer substation. And you can say that the customer substation transfers the heat from the district heating system to the internal heating system of the customer. And then we also have, of course, some different heat demands in a building. And you can say that heat is generally used for two different things. And that is domestic hot water. That is the water that is delivered in our taps and showers. And then we have the space heating, which is the heat that heats the house, the individual rooms. In the building, we also have a heat meter, and this heat meter measures and collects certain values that are used for billing purposes, that is making the customer pay for the heat that it is using. In the heat meter, we measure 4 different values in general. We have the heat consumption, the supply and the return temperatures, and then also the mass flow. And the mass flow is the amount of water that passes through the building. All of these values are gathered from the district heating side of the customer substation, which means that in general, we don't have access to any values from the internal heating system of the customer. And that can be good to keep in mind later on in the presentation. But okay, that was some basic concepts about district heating. Why have I then been working with faults in the district heating buildings? Well, in a real district heating system, you can have several thousands of buildings connected to the district heating system. And of course, all of these buildings will have an impact on how well the system performs in different ways. Previous studies have shown that as many as 75% of the buildings in a district heating system may work less optimally than they actually could. And this is a big problem because what usually happens when a building is not performing as it should is that the return temperatures from the buildings increase. And this is definitely something that we want to avoid in the systems today. Most utilities are currently trying to actually decrease the system temperatures. So of course, we don't want high return temperatures from the buildings. And the high return temperatures, they generally comes from faults that are located either in the customer substation or the customer's internal heating system. So this is the reason why we want to work with faults in the district heating buildings. If we look at some benefits that are related to decreased distribution temperatures, we can see that at the production sites, we can actually integrate more renewable and recycled heat, and we can also increase the efficiency in some production sites. If we look at the distribution site, we can see that the systems are currently experiencing quite large heat losses. And these are mainly due to the fact that the temperature difference between the distribution temperatures in the system and the surrounding is quite high. So if we can reduce the system temperatures, we can also reduce the heat losses. And this is, of course, very beneficial from a system efficiency point of view. So by reducing the system temperatures, we can achieve a district heating system that is more environmentally friendly, but we can also save money. Because previous studies have shown that if we can decrease the return temperatures by 1 degree, we can actually save 0.5 euros per megawatt hour of produced heat. And that is actually quite a lot of money in the end. But what is a fault then? Well, you can say that in my work, the word fault has quite a broad meaning. But in general, a fault is an unpermitted deviation of at least one characteristic property of the system. This means that a fault can be many different things. For example, it can be broken components, but it could also be changes to the settings in the customer substations that makes the building work less optimally. So we want to be able to detect all of these systems or all of these different faults. And one way to do this is actually to use the customer data, because the customer data represents characteristic properties from the buildings. So by analyzing this data, we can actually detect the faults. However, this is not being done to a very large extent today, or at least not in an automated way. So what we have been trying to do in my work is to improve the current fault handling processes in the district heating installations by integrating fault detection methods based on analysis of district heating customer data. And this has been quite a long project, and we have made many different things in this project. It's been a bit of a journey as well. So I'm going to take you on this journey and try to explain what we have been doing in my project. And we're going to start from the beginning, where our initial approach was to try to develop fault detection methods based on analysis of district heating customer data. And we did this in papers 1 and 2. If we start with paper 1, what we did there was that we tried to develop a fault detection approach that was based on a data model of a customer installation. You could say that this method was developed in 3 main steps. The first step was to create a model of a well-performing installation. And what we modeled in this model was the mass flow passing through the substation, because this gives us an indication about the model or the substation performance and the building performance. Then we introduced the model to a data set that was known to contain a fault to see what the model performance looked like for this data set containing a fault. Because our idea was that if the data set that we give to the model contains a fault, the model behavior should in some way change. So the next step, or the last step of this process, was to compare the model performances for the data set from a well-performing installation and for the data set from that was known to contain a fault. We did this using the residuals, and the residuals is simply the difference between the actual value that was measured in the installation and the value that was predicted from the model. So we calculated 2 different residuals, the residual between the actual values and the model output for the well-performing data set, and then the residuals for the actual values and the data set containing a fault, or the model performance for the data set containing a fault. And then we compared these 2 different residuals and tried to see if there were any differences between them. And today I'm going to present the results for 2 of the different faults that we included in this study. One being the drifting outdoor temperature sensor. And a drifting outdoor temperature sensor can be said to be a sensor where the measurement in the sensor increases gradually over time. The figure that you see here is the cumulative sum of residuals. And this may seem a bit fluffy maybe, but the cumulative sum of residuals is actually just the sum of the residuals over time. So we have simply added them over time. In this figure, you can also see 2 different lines. We have the blue line, and that corresponds to the predictions for the well-performing data set. And then we have the red line, and that corresponds to the data set containing a fault. The fault was introduced in August 2016. And soon after this, we can actually see that the 2 lines start to deviate from each other. And after approximately 1 to 2 months, we can actually see that they are quite clearly distinguishable from each other. And this is exactly what we wanted to see, because this gives us an indication that the model performance has actually changed for the data set containing a fault. So our conclusion from this figure is that this approach actually works. However, if we instead look at another fault, that is a drifting supply temperature sensor, we still have the same figure, we still have the same lines and everything. The fault was induced for the same time period. However, now the 2 lines are not as clearly distinguishable from each other. I mean, we can see the difference here today because we can see the red and the blue. But if, for example, trying to implement an automated method based on this, it would probably be hard to tell the 2 lines from each other. So therefore, this gives us an indication that this method actually does work, but it doesn't work very well for all faults. And this means that it may be that we need some sort of complementary methods to actually be able to use this method in practice. If we then continue on with the results from paper 2, what we did here instead was that we used a fault detection method based on automated statistical methods. And this method can also be said to be divided into 3 different steps. The first one being to select a reference case of well-performing installations. Then the second step is to model the average behavior of these reference case installations and create thresholds within which the values of a well-performing installation should be located. This may seem a bit weird when you just hear it, so I have presented it in a figure here. What you see in this figure is the cooling values from the reference case installations as a function of the outdoor temperature. And the cooling is simply the temperature difference between the supply temperature and the return temperature in each building. The middle line, I'm just going to see if I can show you this here. The middle line here represents the modeled average behavior, and then the top and the bottom line represents the thresholds that we created for the model. So this is actually based on a quite frequently used statistical method, which is called limit checking. And what this method does is simply to use the fact that the measured variables from a process should be located within certain thresholds to be considered as being well-performing. So the next step here in this model or method is actually to compare the performance of the other values or from the other installations to the reference case thresholds. And in the next figure, I have plotted the performance or the values from one well-performing and one poorly performing installation. The blue circles here represents the well-performing installation. And as you can see, all of the values from this installation are actually located within the thresholds that we created previously. Then, if we instead look at the poorly performing installation, you can see that the main share of the red circles are actually located outside of the thresholds. And this is then an indication that this installation is probably not working as it should. So, okay, now we have a method that can actually detect deviating behaviors. And we also have the method in paper 1 that can detect deviating behaviors. Our next step would, of course, be to make sure that the methods are actually detecting the installations that have contained a fault in real life. So that is what we try to do. We try to validate the fault detection methods. However, we quite soon realized that validating the fault detection methods was hard, and this was due to the lack of labeled data. And labeled data can be said to be data that has information about what the data contain. And in my studies, labeled data can be said to be data where a specific fault is known to have occurred at a specific time and in a specific building. And to show you the importance of labeled data, I have created a small illustration. Because if we take these two circles, the circles to the left representing the installations identified by the methods, and then the circle to the left representing the installations that actually have contained faults in real life. We of course want these two circles to overlap if we have a method that is working well, because this indicates that we are actually identifying installations that have had a fault in them using the fault detection methods. And of course, we want this overlap to be as big as possible, because a big overlap means that we have a well-performing fault detection method. However, since we didn't really have the right circle, we didn't really know about what installations actually had contained a fault, this kind of validation was really hard. So this is when we started to ask ourselves some different questions in my project. And the first one being, of course, why isn't this label data available today? Well, I think that the main reason to this is the fact that the data that we are using is the data that is normally used for billing purposes. This means that the utilities working with the data, they don't usually use that for data analysis. And this means that even though they find fault instances in their systems, they don't seem to see the reason to connect the fault instances to deviations in customer data because they don't need this connection. However, in my work and in other people's work that are working with fault detection in this kind of systems, we need the connection. So the next step was to consider how can we actually obtain the label data? How can we make the utilities work so that we can obtain label data sets? And this is where we decided to shift focus a bit in my project and instead try to learn more about the current fault handling processes to figure out if we can gain the label data from the current fault handling processes, and also if we can find good working methods that the utilities are currently using in the fault handling processes. The first step in this was to investigate what the most frequently occurring faults were in the current district heating systems. And we did this by sending out a survey to the district heating utilities in Sweden. We got some interesting statistics based on this, which is represented in this figure here. And as the title of this slide says, these statistics represents the most frequently occurring faults as experienced by the district heating utilities. This means that this is not the actual count of the faults in the systems. However, these are the faults that the utilities experienced occurred most frequently, because the utilities, they in general don't have the actual count of the faults that occur in the systems. But I still think that this figure is very interesting, because in the figure, we can see that leakages corresponded to the largest share of the value. Then we had faults in the customer's internal heating system, which also corresponded to a very large share of the faults. Then we also had faults related to the control valves, the actuators, the inferior gaskets, control systems and controller, and also the heat exchangers. What I think is really interesting in this figure is, however, the fact that such a large share of the faults occur in the customer's internal heating system. Because the internal heating system is a part of the system or the building that the utilities in the normal case don't have access to. And this means that there is a large share of the faults that the utilities can't access and fix today. So in the future fault handling processes, it is important to keep in mind that we should probably have access to the customer's internal heating system too, and not only the substations, as is usually the case today. But okay, now we had looked at some of the most frequently occurring faults. As I mentioned, we also wanted to look into how the utilities are currently working with fault handling. And of course, we were specifically interested in how utilities that are actually successful in fault handling are working. So we looked at the utilities that already had low return temperatures in the systems, because we figured out in the studies that they have actually managed to eliminate many of their faults in their customer buildings already. And today I want to present some of the aspects of their successful fault handling processes. The first one is that all of the utilities that were working in this way had very close customer relationships. They worked actively with their customers. They made sure that the customers understood the value of eliminating faults in their system, and therefore the customers were more willing to work with faults in their buildings. The next step was also that they conducted a lot of regular maintenance visits, which means that they went out to their customer buildings on a regular basis and made sure that they were working as they should and did not contain any faults. They also had created clear incentives to their customers about why it is important to eliminate faults in their buildings. The most common solution to this was to introduce some sort of monetary or economic incentives so that the customers had to pay for the faults that were present in the buildings. But other ways was also to just provide them with a lot of information about why this was important. And then last but not least, they were also working with fault detection in different ways. Some of the utilities performed manual data analysis, for example, but many of the utilities stated that the most common way to detect fault today were actually during the maintenance visits that they performed. And this was not really the ideal case, they would say. They would want to have these more automated fault detection methods that can detect faults more rapidly and on a regular basis. So when having found all of these aspects of successful fault handling processes, we of course wanted to see how we can implement the knowledge that we have found during my studies in the future fault handling processes. So therefore, the final step of my project was to investigate what in the fault handling processes could be improved, and also to develop some actual solutions to improve the processes. The first thing that we did then was to sit down and think of, okay, what would the ideal fault handling process based on data analysis look like? And I'm going to present our initial idea to you now. The first step is that we have some sort of data analysis. We have a data analyst that analyzes the data and looks for fault in the data sets. If something looks weird in the data, a technician, a service technician, is sent to the building and investigates the building to see if there is something wrong. Let's say that the service technician finds something, then he or she creates a report of what was actually found in the building. And then this information is reported back to the data analyst. This process seemed quite simple. And when starting to talk to the district heating utilities that are interested in using different fault handling processes and fault detection methods, realize that this is a simplified way to represent this process. There are, of course, many different steps in between the steps that you see here, and there's a lot of information that is needed for the fault handling process. So to investigate this further, we conducted a workshop where we talked to a number of district heating utilities, and we identified some of the main problems that have to be solved if we want to use this kind of workflow, and also if we want to improve the workflow. The workflow that we have worked with and conducted the workshop about is quite complex, so I won't go through it in detail today, but I'm going to present the main problems that we need to solve in the workflow. The first one is that the fault detection today is inefficient. As I said previously, the main way to detect faults was by actually visiting the customer installation and finding out that something was wrong. Of course, we want to find ways to find the faults before actually going out to the buildings as well. Then the level of automation was not as good as it could be. This would be improved by including, for example, the automated fault detection methods, but also to include other things such as digitalized service protocols and having better communication strategies within the utilities. Then the next point of improvement was also the maintenance agreements. One way to improve them would of course be to have access to the customer's internal heating system so that we can fix the faults there. But it would also be very valuable to change the maintenance agreements. For example, to have what is called predictive maintenance. And predictive maintenance is a maintenance scheme that is based on predictive fault detection methods. That is a fault detection method that identifies when a fault is about to happen, so that we can actually fix the faults before they have had a big impact on the system efficiency. Then, of course, we could also see that the organizational structure of the fault handling processes is really important. Today, fault handling is mainly being done when there's time to spare within the utility, and not maybe when it's needed the most. So one way to do this is to have someone that's actually in charge of the fault handling processes, a stakeholder that is responsible for the work being carried out on a regular basis and making sure that it is followed up as well. And then the last point that the utility stated that they wanted was also a standardized way to do their service protocols, because they thought that today they don't have this standardized way of doing this, which means that if one person goes out to a building, he or she fills in the report in one way, and then when the next person goes out to a building, he or she fills in the report in the next way, in another way. And this is not good, because then we don't get the information about the data or information about the faults in the standardized way. And this is something that we want in the future, especially when developing fault detection methods, because we need the information about the data, that is labeled data, in a standardized format to develop well-performing fault detection methods. And this last point here is something that we investigated further in paper 4, where we developed a deviation cost taxonomy. And a deviation cost taxonomy can simply be said to be a classification system for different faults. So the deviation cost taxonomy consists of a number of different fault labels that contains information about faults. This taxonomy consists of a lot of information, which I won't have time to go through in detail today, but I'm going to present a simplified version of the taxonomy so that you understand what it contains and how it looks. And I will go through it by using an example fault. And the example fault that I picked out is that there is a broken supply temperature sensor in the heating system of a building that has been fixed by a service technician visiting the building. The first level of the taxonomy is called cost of deviation. And this level describes what is the actual cost of the deviation that we have seen in data. For our example fault, there was a broken supply temperature sensor in the heating system. So the cost of deviation is fault in the heating system. The next level is called component, and this describes which component it is that is being faulty. In our case, it was a broken supply temperature sensor. So here we write supply temperature sensor. The third level is called fault description, and this describes what is actually wrong with the component. In our case, the temperature sensor was broken, so the fault label in level 3 is broken. Then we have the fourth level, which is called action, and this describes what has been done to actually fix the fault. In our case, the temperature sensor was replaced, so we have actually changed a unit in this case. And then the fifth and last level of the taxonomy is called status, and this describes whether or not the fault has been fixed. And in our case, of course, the fault was fixed, so it has been handled in the building. What you see here is a fault label that we can use for many different things. For example, we can use it to create more advanced statistics about the systems. We can also use it, of course, to label our data. And this is exactly what we think that this taxonomy can be used for, to create the label data sets that we want to be able to validate and develop more accurate fault detection methods. So that was the main results from my thesis work. And to finish my presentation, I just want to present some conclusions that I think will bring us closer to spotting the differences in the district systems. First of all, we have seen in our studies that we need automated fault detection methods. The utilities are very interested in using them, and they want to implement them as soon as possible, really. What is really nice to see in both mine and other people's research as well, that is also working with fault detection in this way, is that the fault detection methods may be developed using the existing customer data. This is really nice because this means that we can actually implement the fault detection methods in a quite rapid way, actually. And it also means that we don't have to install, for example, additional sensors or other equipment that has to be used to measure more things in the system. And this is, of course, good from a cost perspective. The second thing is that the fault detection methods are really important. However, I believe that their implementation is even more important than the fault detection methods themselves, because the methods, they have to be used on a regular basis. We have to use the results from them and actually make sure that we are identifying faults using them. And so we need to look at how we are working with faults in our district heating systems today and how this can be improved. And I think that the workflow that we have developed in my studies may be a good help in this work in the implementation of the fault detection methods. Last but not least, clear stakeholders and organizational structures are also needed to succeed in fault handling. As I said previously, fault handling today is mainly conducted when there's time to spare within the utility. And this is not good enough. We need to have someone that follows up on the fault handling, that makes sure that fault handling is carried out on a regular basis, because this will make it a lot easier to work both actively and systematically with faults, and also in the long run to actually eliminate more faults in the systems. So therefore, I think the main point that I want to emphasize from my work is that a holistic approach to fault handling is needed. I mean, of course, the fault detection methods, the taxonomies, and different organizational structures are really important pieces to the puzzle, but we need to see the greater picture of the fault handling processes to be really successful in eliminating and spotting more differences in the system. That was what I wanted to present today. Thank you very much.